Hey everyone, welcome. So today we're going to explore the surprising and honestly kind of fascinating science hiding right behind our daily physical chores. We're looking specifically at the physics of work, energy, and simple machines. By the end of this explainer, I promise you'll look at lifting a box, pushing a grocery cart, or literally just sweeping the floor in a completely new, scientifically empowered way.
But before we get into the mechanics of making those chores easier, I have a quick question for you. Picture this. You walk up to a solid brick wall and you push it with all your might. You push and push until your muscles are aching, you're sweating, you're totally exhausted. According to physics, how much work did you just do? Hold on to your answer because the scientific truth here might actually shock you.
Okay, let's dive into this. Here's our roadmap for today's explainer. First, the scientific definition of work. Second, calculating total work done. Third, when work equals zero. Fourth, energy as the capacity for work. And finally, number 5, how simple machines help.
Starting with Section 1, the scientific definition of work.
To set our foundation, let's look at how science actually defines work. You know, in everyday language, we say we're doing work anytime we feel tired. But in science, work has a highly precise meaning. It's strictly defined as the product of a constant force acting on an object multiplied by the displacement of that object in the direction of the force. Simply put, work equals force times displacement. So if you want to do scientific work, it's not enough to just apply a force, you actually have to move something a specific distance.
Moving right along to Section 2, calculating total work done.
Let's look at how we measure and scale this work in practical, real-world situations. Notice how beautifully logical physics is when we scale things up. Let's use a super common task, lifting bags of wheat. Imagine you slowly lift one 5-kilogram bag of wheat exactly 1 meter off the ground. To do that, you apply an upward force to overcome gravity. Boom, that's your base amount of work. Now, what if you lift 3 bags of wheat at the exact same time to that same 1 meter height? Well, you need to apply 3 times the force, so logically, you're doing 3 times the total work. But what if we go back to just 1 bag, and instead of lifting it 1 meter, you lift it 3 meters high? You're applying the same base force, sure, but over 3 times the distance. So once again, you do 3 times the work. Total work done is perfectly determined by scaling either the force or the distance.
And because science loves standard measurements, we actually have a specific unit for this. When you multiply a force of 1 Newton by a displacement of 1 meter, you get 1 joule. The joule is the official standard unit of work. So anytime you're calculating the force you apply over a certain distance, you are literally calculating the joules of work you've just accomplished. All right, Section 3. This is a fun one. When work equals zero. Let's revisit our paradox from earlier. Notice the boy pushing that solid brick wall until he's completely exhausted. Because the wall didn't move, meaning the displacement was strictly zero, the total scientific work done is also exactly zero. Crazy, right? Physics doesn't care that his muscles used up internal energy. No movement means no scientific work. But now, look at the girl carrying the box. She's applying an upward force to hold the box against gravity, but she's walking horizontally. Because the force she applies is perpendicular to the direction the box is actually moving, the work done on the box by that upward force is also zero. It's a fantastic, kind of mind-bending reality of physics. You can be carrying a massive box across a room and scientifically be doing zero work on it in that vertical direction.
Which brings us to Section 4, energy, our capacity for work. If work requires force and distance, what actually fuels this work in the first place? Well, that's where energy comes in. Energy is quite simply defined as the capacity to do work. Think of it as the currency of the physical universe. You literally cannot do work without spending energy. And because they're so intimately linked, energy shares the exact same unit of measurement as work, the joule. Whether you're using electrical energy to rotate a fan or chemical energy from your breakfast to lift those bags of wheat, energy is the essential requirement.
In fact, they're essentially 2 sides of the same coin. This is known in physics as the work-energy theorem. It states that the work done on an object is perfectly equal to the change in its energy. When you do positive work on an object, like, say, pushing a heavy cart, you're actually transferring your energy right into that cart, giving it kinetic energy. Doing work is really just a mechanical way of transferring energy from one thing to another.
And finally, Section 5, how simple machines help. This is basically the physics cheat code. So we've covered the rigid rules of force, distance, work, and energy. But what if a chore is simply too heavy for us? Imagine you have a massive, awkward load that needs to be lifted to a certain height. The physics says lifting it requires a fixed amount of work, a set number of joules. You can't change the laws of physics, right? But how do we make that exact same task feel significantly easier on our bodies? The answer lies in simple machines.
To understand why machines are practically magic, we need to understand mechanical advantage. This is mathematically defined as the ratio of the load, which is the heavy force you need to overcome, to the effort, which is the force you actually apply to the machine. A machine with a high mechanical advantage allows you to input a very small effort force to move a very large load force. But how exactly does it do that?
Take a ramp, for instance, an inclined plane. Remember our golden rule, work equals force times distance. If you need to do a fixed amount of work to get a heavy block up to a certain height, you can either lift it straight up, which requires a huge force over a very short distance, or you can push it up the ramp. The ramp dramatically increases the distance you have to push, and because you increase the distance, you proportionally decrease the force required. You spread the work out. You do the exact same total amount of work, but the ramp makes the effort force feel incredibly easy.
Another amazing simple machine is the lever. To understand a lever, you just need to know its three main parts. First, the fulcrum, which is the fixed point the lever rotates around. Second, the load, which is the heavy object you actually want to move. And third, the effort, which is where you push or pull. By simply changing where these three parts are located relative to each other, a lever lets a tiny little force move a massive object.
And we actually categorize levers into 3 classes based on what sits in the middle. In a Class 1 lever, the fulcrum is in the middle. Think of a seesaw or a crowbar. In a Class 2 lever, the heavy load is in the middle, like a wheelbarrow, where your effort at the handles easily lifts a huge pile of dirt. And in a Class 3 lever, your effort is in the middle, like when you use tweezers or sweep with a broom. We use these arrangements every single day without even realizing we're exploiting mechanical advantage.
So we absolutely must remember this fundamental truth. As the source material beautifully puts it, machines do not create energy, they only help us use it more effectively. The total work done remains exactly the same. You cannot cheat the universe out of joules. But by using an inclined plane, a pulley, or a lever, you trade distance for force. You spend your energy in a way that is vastly more convenient for your human muscles.
We've unpacked the real scientific meaning of work, the currency of energy, and how simple machines manipulate force and distance to make our lives infinitely easier. So I want to leave you with this little challenge. Look around your house right now. What simple machines are hiding in plain sight in your kitchen drawers or out in your garage, quietly giving you a mechanical advantage every single day? Keep an eye out for those everyday physics helpers, and I'll see you in the next explainer.